we will discuss about the imperfection or defects in the metal and the crystal. Okay. So actually for the chapter 4, okay, solid solution and the crystalline imperfections. For this one, Doctor, what is the test syllabus? Syllabus test. I think we cover CLO1 as well as CLO2, maybe. Please look at the CLO, your course learning outcome. Please refer that. Refer to the course outcome. Okay. So what's the topic that we're gonna discuss for in the chapter 4 is a type of the solid solution. Okay. And defect in the crystalline solid, which is mostly we cover, I think, is point defect and line defect or dislocation. I think it's, uh, 0D or 1D as well as 2D. I'm not sure we cover or not for 2D. Okay, but we will not cover for 3D defects, I think. Okay. And in the textbooks, actually, we cover section 4.3 to 4.4. So we're not going to cover all the topic in the chapter 4. Okay, just some part. Okay, about the imperfection or defects. By the end of this course, I hope that you can be able to define what is the definition of the solid solution. Mainly, we focus on the alloy. Okay, distinguish of the type of the solid solutions. Okay, describe the crystal defects. Okay, there's many defects. Okay, and such as interstitials. Okay, what else? Subtitulars. Okay, all those type of defects. And explain the influence of defect on the properties. Okay, actually, the influence of defect also important for the properties of the material in terms of resistivity. Okay, mechanical. Okay, electricity is important because it is quite rare to have what is it, the material which is really pure. Okay, only some 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 material we can use pure like a decorations or for the electricity purpose. Okay, but it's quite rare actually. Okay, okay. So a very few metals that yes, I told you that there are very few metals that used in the pure or nearly pure state. Okay. For example, as I told you, like a decorative purpose, right? The you use a high purity of aluminum, 99.9%, okay, or super pure aluminum, because we use as a pure because we want to see that that material is a very bright or metallic surface. Okay. What else? Like a copper also, okay, pure copper, 99.99%, okay, used for the electronic devices. Okay. So that is for the pure material, but actually it's a quite rare. It's very few. Okay. And uh, in terms of engineering, okay, most of engineering metals we combine with the metals or non-metals, okay, because we want to have or provide some like a properties to increase the strength, okay, higher corrosions, okay, resistance, and then we want other desired properties also, okay, like what can conduct the electricity much better than pure materials. Okay. So for alloy or known as the metal alloy is we we, we can define as a two or more metals. Okay. Or non-metals. It is a mixture. Okay. Two or more metals or non-metals. Okay. This is alloy. There is a two type of the alloys actually, which is a simple cartridge brass. Okay, so this one is a binary alloy, about 78% copper and 38% zinc. So this is the simple alloy. But also we have another types, okay, which is complex. If you know this one on the left side is the incordance we use to measure the what is it, heat or temperature. Okay. Or nickel based super alloy we use for the jet engine part. Okay. So this one is content of the 10 elements of composition. Okay. So this is, you have to remember the type of the alloy. Okay. So the simplest type of alloy is we call it as a solid solution. Okay, contains two or more elements dispersed in the single phase structure. So for example, if you look at this figure is uh, this one is a solvent. Okay, the black one solvent, or we call it as a host or parent atoms. Okay, so this one. Okay, and the red one is the solute. Okay, so that means contain two or more element dispersed in the single phase structure. Okay, this is the definition of the solid solution for the metal or non-metal. Okay, so in generally there are two types of the solid solutions. Okay, substitutional as well as interstitial. Okay, so if you look at here that for the substitutional is the solute atom. Okay, the solute atom displacing the atoms of the solvent or the host. And generally, for the solute, they have a large the what is it? The size is larger than the solvent. Okay, for example, this one ferrum, iron as well as chromium. Okay, iron as a host, while chromium as a solute. Okay, so another one is a interstitial solid solution. Okay, this one is a solute atoms located between atoms of the host, which is if there is a void between parent atoms, so the small atoms or solute will be located between the parent atoms. Okay, for example, this one. Okay, ions. Okay, as a host atoms, and this one is a solute. Okay, so it can be located in the middle of between carbon atoms. Okay, so some reason is because of we want to maintain the charge or neutrality. Okay, that is one of the reason. Okay. Okay. So let's see the substitutional solid solutions. Okay, if you look at here, that the substitutional solid solution is the which actually is a form by the two elements. Okay, solid atoms can substitute for the parent atoms. Okay, in the crystal lattice. Okay, and crystal lattice or crystal structure of the parent elements remains unchanged. Okay, and the lattice also can get distorted. Okay, because of different in the diameter. Okay, but to see the 100% of the solubility between two atoms or non-atoms and non-metal on metals. Okay, so we can use home rotary rules. Okay, so solute percentage in solvent can vary from the fraction of the percentage to 100. So that means can be 0 to 100%. Okay, can be solubilized until it 100% solubilized. Okay, so it should be follow the home rotary rules. Okay, home rotary rules is to see the condition that either the solubility is favor or not between one element with the another. Okay, so what is the rules? So this is important. You have to highlight this one. Okay, first rule is diameter of atom must not differ uh, more than 15%. Okay, so you have to remember between two atoms is must be below than 15% or equal. Okay, and the crystal structure of both element must be the same. Okay, what do you mean by crystal structure of both element must be the same? Anyone? What is the meaning of crystal structure of both element must be the same? Anyone can answer? What do you mean by crystal structure?
Is it like the FCC BCC?
Yes. Okay. If uh if the crystal structure have a BCC, another one also have must be BCC. Okay, BCC and BCC, FCC and FCC. If different, it's not going to be favorable. So that means your percentage, the solubility of the percentage of the solvarizations between two atoms, okay, or two crystal, okay, between solvent and also solute is gonna be below than 100 or maybe below than 50%, okay. And then no appreciable difference in terms of electronegativity. Okay, that means almost similar electronegativity. Okay, between two elements. Okay, and then both elements have same valence. Okay, for example, 2 plus must be equal with the 2 plus. Okay, 1 plus must be similar with 1 plus. This cannot be different to get 100% of. So in order to get 100% solubility, is must be satisfied with all these rules. Okay, from rule number 1 until number 4. Okay, for example, if you look at here that copper and zinc, okay, they have a solubility around 38.3%. Okay, and then electronegativity difference is around 0.1%. Okay, atomic radius is just atomic radius is below than 3.9%, but it still have a solubility of about 38.3%. So that means maybe there's another rules that cannot be satisfied by for the copper and zinc. Okay, for example, copper and lead. Okay, copper and lead, if you look at here, the atomic radius is 36.7, right? So if you look at here, C is more than 50%. Okay, that why the solubility is just at 0.17 between solute and solvent. Okay, but if you look at the copper, okay, is below than 50%, and atomic is zero. Okay, 100% solubility. Okay, so if you want to see more, okay, why is 100%? So we can see the examples. Okay, so if you look at here, for the Cooper, okay, so just follow the rules. How to get 100% solubility. Okay, and look at here that this is the solute, this solute, this one is the solvent as a parent atom. Okay, so rule number one, the radius, right? Rule number one, the diameter atoms not differ than 15%. So what you have to do is you use this equation, R solute minus with R solvent divided by R solvent or radius. Okay, and times with 100. We can see here that this one is for the solute or for the nickel. Okay, minus with diameter copper for the copper and divide by the solvent also. So we can get negative 2.3% or below than 50%. So this is favorable. Okay, follow. So it's satisfied rule number one. Okay, another one is a copper and nickel. Okay, they have a similar crystal structure. Okay, so that is good. Okay, so it's also favorable. How about the electronegativity? If you look at here that copper and nickel, right? There's a almost similar electronegativity, different 1.0, 1.8 as well as 1.9. So it is also favorable. And same valence, copper and nickel is plus 2. Oh, sorry, just now I said 2 plus, right? It should be plus 2 or minus 2. Is the charge about valence, right? Okay, so that why this is a very high solubility, okay, for nickel and copper. Okay, so let's see if a solid solution is not really favorable. Okay, some rule is not satisfied. Okay, if you look at here, copper and zinc, right? Why is the solubility is just below than 50%? Okay, look at here that yeah, is it favorable below than 50%? Unfortunately, they have a different crystal structure. Okay, zinc is HCP hexagonal, cubic. I don't remember HCP. Okay, please refer to the previous slide. And FCC, face center cubic, hexagonal center. I don't remember this, but it's different because we're not covering this chapter, right? Okay, so this is not favorable. Okay, in terms of electronegativity is almost similar, favorable. Okay, zinc and copper is a plus 2. Okay, since one rule is not satisfied, that's why the solubility is just 38.3%. It can be achieved at high temperature, even you increase the temperature. Okay. Okay. Any question about this Hume rotary rules? I hope everybody can understand. Any questions? The important part before we have tutorials. No, so far, okay, it's good. Okay, that's good. Okay, later you have to do some tutorial based on the home rotary after 2 slides. Okay. So another type of solid solution is the interstitials. Okay. Solid atoms fit into the spaces between the solvent or parent atoms. Okay, we call it as interstices. Okay, space or holes. Okay, there is a hole right between the parent atoms. Okay, look at here, there is a hole. Okay. So solute atom generally is smaller than solvent atom. For example, like hydrogen, carbon, nitrogen, or oxygen. Okay. And interstitial, for example, this one is interstitial solid solution for the carbon in FCC gamma ions. So if you look at here, that carbon is just 0.075. Yeah, this one, 0.075, and iron is 0.129. So that means this carbon can fit into the space between the ion atoms. Okay, so the maximum of 2.08% carbon can dissolve interstitially in gamma ion. Okay, so this is the good example for the interstitial solid solution. Okay. Okay, so what's the difference, the comparison between interstitials as well as substitutionals? Okay, two possibility when metals are alloy. Okay, when you alloy, first possibility is which is a substitutional solid solution, which is foreign atom of solute replace host atom. Okay, in orderly or random arrangement. For example, this one copper and nickel, zinc, okay, zinc and copper. Okay. This one random copper and nickel, order nickel, aluminum alloy. Okay. Interstitials, okay, parent foreign atoms or solute goes into holes or voids. Okay, so it can fit into the between parent atoms. Okay, either orderly or random arrangement. Okay, so this is the example for random arrangement and order arrangement. Okay, for example, silicon, carbon, as well as iron. Okay, in for order arrangement is clay, ionic crystal, as well as ceramic. Okay, so there's two example of the solid solution, interstitial as well as the what is it, substitutional. Okay, so let's I think all of you have to do example. Okay, example one. Okay, by using the Hume rotary rules, okay, can you predict the relative degree of the solid solubility of the following element in aluminum? So that means aluminum as uh, parents parent atoms, and elements A until E as a solute. Okay, use the following scale. Okay, very high 70% to 100%, high 30% to 70%, moderate 10% to 30%, low 1 to 10%, and very low below than 1%. Can you do this one by using home rotary rules? Okay, can you predict the degree of the solubility? Okay,
Doctor, very high mean can soluble easily.
yes, it can. You can see in terms of atomic radius. You can see in terms of electronegativity. Okay, just I think it's not really by using home rotary. Okay, even if you just observe based on the atom radius and also the crystal structure, electronegativity, I think you can predict also. But it is good or better if you use the home rotary rules to predict. For example, just right now, copper and nickel, right? It's become 100% because it's satisfy all the regulatory rules. Okay, and you do? I want to give the what is it? A link for the Padlet. You can see right the questions, or you can download my PowerPoint slide from the e-learning Padlet, and then you paste in the Padlet. You have to construct the tables. Okay, you have to construct the tables, and then you have to predict. So that is the link for the Padlet. For example, this one, Cooper and aluminum. Why my answer is Cooper as a parent? Let me check. Sorry. Zinc lead. I think this is. Oh my god. Let me check. My answer I did for Cooper actually. Cooper. It's okay. Just follow this one. Okay. Zinc silicon. Okay. If you done, please post in the Padlet. You can discuss with your friend. It's possible. But one post already. So, for example, actually I don't have the answer. Maybe I have or not. Aluminium, because I just did it for the copper. Okay, so if you do, if you make a table, if you make a table, so this one is the system, aluminium, and what is it? Number one is copper. Okay. Number two, aluminium with manganese. Uh, okay. And then number three, aluminium with magnesium. Okay. So this one is the system. Can you predict? What else? What you have to do is, can you calculate the atomic radius difference? Okay, delta R. How many percent? All metal, or all system. Okay, until silicon, aluminum. This one copper, aluminum with copper, aluminum with the manganese. This one is aluminum with the magnesium, zinc. Okay, this one is for zinc, silicon. Okay, and then
I wanna ask,
yes.
uh, how how can we know which one is solute and solvent?
Which one is solute? Which one is solvent? Which one? Which one?
Aluminum and
Yalah, aluminium and copper lah. Aluminium dengan copper mana satu yang solvent, mana satu parent? Which one?
dia based on radius yang besar.
Tak semestinya. Kalau kat sini, predict the relative degree of solid solubility of the following elements in aluminium. So this one is parent lah. Yang ni solid lah kan. Selalunya kita akan tulis yang sebelah kiri ni. On the left side is the parent atom. Right side is as the solute ataupun foreign atom. Okay? Boleh?
Okay.
Okay.
Thank you, Doctor.
So this one is first rule about the electronegativity difference. Atomic radius difference, sorry. And then electronegative difference. Okay. You have to list down. Okay, what else? Maybe type of crystal, right? This one. Type of crystal. Number 4 is, what is the number 4? Number 4, crystal structure, right? Isn't it? I don't remember. Yeah. Okay, 1, delta R. Oh, number 2 is, sorry. This one, number 2 is gonna be, this one is gonna be number 3. So this one is crystal structure. Okay, what is the crystal structure? And this one, electronegativity difference. Okay, valence. Okay, see the valence. 4 rules. And then, what is your prediction? What is your prediction? I have no answer actually. So based on your what is it? Your knowledge, and also some what is it? Based on this rule, okay, which one is have a high solubility, okay, and which one have a very low solubility? Please post in the Padlet, okay. I hope you can make like make a table like this one, so that you can compare, okay, easily do the comparison for all the system. Okay, so we have, I think, 1 2 3 4 5, okay, 5 systems. Oh, 5.
Doctor, what is the favorable difference of electronegativity? I mean, like,
Tengoklah dia punya ni, almost similar, right? Must be almost similar. If you think that one is have electronegativity too much, so it's not favorable. I cannot say. Generally, is almost similar, like 0.1, 0.1, or 0.2, 0.3 is still acceptable, I think, below than 0.5.
Okay.
But I cannot. How about the? I'm not sure. So let me. So I think the difference is not really. It should be appreciable. Okay, not really. Tak terlalu besar lah beza tu. Right. Itu macam buat error tu kecil lah. Something like that lah. Okay, please do this kind of table, okay? Oh, dah 4:38 dah. Anyone? Anyone already post? Not yet. Okay. So what is your prediction actually? But to get yes, but to get the exact percentage of the solidity is, of course, we have to do the experiment. That's the main one of the method lah, if you want to confirm. Okay, anyone already? How about A? What is the I think you have to compare for all 5 system, right? Anyone want to show the answer? Okay, I think yeah, today we just until example 1 or example 2. And then next, tomorrow we discuss on the rest about the crystalline imperfection. Okay. So I give you about another 10 minutes. Okay, or 5 to 10 minutes. I think I have to go also. I have no answer actually. Number one, delta R. System structure. Electronegativity equals 1, 2, 3, 4. What else? Balance. Balance. Negative. Anyone already done?
Sikit lagi dulu.
Aluminium. So, the structure aluminium, copper, aluminium, acid, 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 copper, acid, Done. Anyone? One. Let me see. Let me share with for aluminium. Okay. Share with you. Share. Lukman, hi. Structure is the same, Lukman. Balance plus 3. Plus 3 plus 2 is almost not favorable. Structure is the same. Is it the structure is the same? Structure,
Same dok.
aluminum and copper FCCR is the same. And then 0 electronegativity, 0.3. No valence. And then very low. Yes, I think aluminum and manganese is very low. This one 11.9%, yes, below the percent. Probability 0.2. Plus 2 not favorable. Okay. Difference, I think it's also is quiet. Wait, I think it's a low or it's satisfied too, right? This one satisfied too. This one is satisfied too. 1, 2, 3. Okay. And then this one, 1, 2, also not favorable. So this one, this one may be okay. Different, yes, this one is I think is very low, very low. Okay. This one is I think is very low. Number 3. Number 3 HCP and FCC. FCC. This one also right. Okay. So this one we can consider high. Okay. And then I think we can consider this one also low, I think. Isn't it? I'm not sure the answer. Okay, this is just on the prediction. But to know the answer, of course, we have to see the experimental data. Okay. So thank you, Lukman. I think it's correct. So you understand. Okay. So I don't think there is a is it high or not? Okay, it's 0.2. This one. So this one is already out from the first rule, I think. So we cannot. I don't think so we can mix. Okay, very low solidity. I think it's very low, below than 1%, because the first rule is already out. Okay. Okay. Any more questions? Okay. So it seems like aluminum and copper is high. Okay, some difference also. I think this one is gonna be maybe we can consider as a low also. Okay, low or moderate. Okay, low or moderate. This one also maybe low to moderate. Okay. Okay. Any questions? Thank you, Lukman. Anyone else who want to show the answer? I'm not sure for the answer actually. Okay. But based on your prediction, maybe it's correct. Okay. Because it's just a prediction. What else? Oh, this one. Who's this? I cannot see. Upside down. Okay. Very low, moderate, very low, very low. All is very low. Okay, who's this? Faisal. Why is all is very low? Almost four system. Okay. Four system is all very low. I don't think so. But you have to consider if satisfied maybe 2 rules or 3 rules. So if you can consider it maybe moderate. I don't think. Okay.
No, but because doctor, most of them I got negative value, so I assume that it's all very low.
No, we're not consider the negative value.
I'm not
Okay,
sure.
it's just 15%. Okay.
Mm, okay. So
Okay.
I have a mistake there, right?
Okay. Okay. Anyone else before we stop? Okay, so I think everybody already understand about the home regulatory rules. Okay, so tomorrow we continue on the crystalline imperfection. Okay, any questions? I hope you can master these home regulatory rules. Okay, generally, maybe for test or final, it's gonna be this kind of equation, this kind of question. Any questions? Tomorrow maybe we will discuss also example too. Okay. Any more questions? So if no questions, okay, so we continue tomorrow. Okay, so I think chapter 4 and chapter 8, I think. Okay. Well, we will see tomorrow. Okay, that's all. Thank you, guys. Okay, we'll see you tomorrow. What is the topic of test one? I'm not sure for the topic test one. I will check first. But I think we're gonna cover CLO1 and CLO2. Okay, just refer what is the CLO1 and CLO2. Okay.
Thank you, doctor.
Okay. See you. Anyone still have not scanned the QR code? Thank you very much.
Thank you, doctor.
Okay.
Doctor, I want to ask one things.
Yeah.
The test one is 2nd December, doctor.
Yeah. Second, right? On Wednesday.
Wednesday. Okay, doctor. Okay.
Okay.
Thank you.